Although we have completely modified the Mavrik to allow it to fly, I will show you now some of the faults we found in the original design, as I told you in my previous email. Well, I will start with mechanical faults, and then we will go into the structure of the frame and some troubles of aerodynamic interferences. Well, as you can see here, we've got now an acceptable landing gear. The previous one was made of a rod of around 5 millimeters of carbon fiber. This drone with the present onboard instrumentation weighs 9.5 kilograms. It doesn't make sense at all to use here a 5 millimeters rod of carbon. In fact, it was a broken leg in every landing. What you see now are some of the carbon tubes that were used to hold batteries and gimbal that I cut to put the battery under the center of gravity of the drone. And then instead of throwing it to the trash, I use them to build the landing gear. Let's go to some details. I don't know if I will be able to show it from you. I don't know if I will be able to show it from here. Mechanical tolerances are an absolute disaster. Look at this. This aluminum holder is bigger than the tube. So here it is completely screwed, and we cannot even tighten more that metal holder. These plastic holders that hold the leg in the right place when it is not folded are also bigger than the tube. So I had to use very strong adhesives in both places to prevent the movement of the legs and the tubes where the motors are installed. It doesn't make sense for me. Of course, it should be correctly designed, and here we shouldn't need to even, as you can almost appreciate, to break the carbon because of tightening really strongly the nuts that hold everything. So this happens everywhere. If you go to the other part, you can see he had to use even double-sided silicone tape to fill in all these gaps. So this is an absolute disaster. Let's go now to the design of the frame itself. Well, the reason to design this asymmetrical structure is only justified to facilitate the folding of the drone, which in fact is really good. But it doesn't make sense. You can see in the next photograph a DJI Neo product which also uses coaxial motors, where the symmetry of the whole thing, of the whole aircraft, is perfect. So in this case, we've got a very strong symmetry. You can see that it is a very short from this side to this. It is a very short drone from this side to this side. However, it is really long if you look at it from the front. It creates a trouble that can be, of course, corrected by means of the flight controller. But why doing this in a so strange way if it is not necessary? If you see my video about vortex interferences, you can see here both motors are really close, and this distance is really short, and we've got a vortex interference. Vortex created by this set of motors converge with the vortex created by this other set of motors. The result is less aerodynamic efficiency and a much noisier drone. So this distance should be the one I show you in my video. This data of the other video, where I explain dihedral for the motors and coaxial configuration and vortex interference and blade vortex interference, is taken from PhD studies. So this doesn't make sense. You can only find so close propellers in this design of Steadidrones. And of course, I'm not going to talk about what I told you in my first video about the mass distribution, the huge battery on the rear part and the front part with all the camera weight and so on is something that is absolutely crazy. Well, now in the next video I will show you all the modifications, and you will also see flight test, onboard instruments, because now it is completely functional and we are working with it in our research project.